Hi, everybody. This is lesson 4 in Math 100, Liberal Arts Mathematics. Okay, this is the last of the 4 lessons from chapter 1. Next time we'll go into lesson 5, which is in chapter 2. Chapter 2 in the book, and it has a lot more traditional arithmetic or mathematical elements such as percentages. All right, and big and large, small and large numbers. But before that, we have one more lesson from chapter 1, and that's on problem-solving strategies in general. How do you solve, like typical problems, mathematical problems, non-mathematical problems, mathematical or non-mathematical problems in life, And so this will be a general sort of thing, although the emphasis is, of course, somewhat mathematical. All right, so how do you solve problems? Okay, well, let's find out. Here we go. Okay, so I hope you have printed out the handout of lesson 4, and you should have 2 pages. And then after that, you should be, of course, going into worksheet number 4. And worksheets are typically, you see the deadline in Canvas. All right, so lesson 4 is about problem-solving strategies. And I say recognize patterns because this is really where mathematics begin, right? So people have recognized different patterns, whether it's patterns, sort of with numbers, or patterns of animals migrating, or patterns of temperatures going up and down, or patterns of population growing or going up and down, and, virus spreading. All kinds of patterns. And what mathematics tries to do is to model those patterns using the language of mathematics. It's typically an equation or inequality or functions or something, or graphs. And so it is really at the heart of mathematics. Throughout this chapter 1, you may have been feeling, hey, I signed up for a math class and I really haven't done much of calculations. Well, if you happen to miss calculations, great, because starting in chapter 2, you will be doing lots of calculations of numbers, but still the emphasis on practicality and recognizing patterns and using mathematical patterns and rules to solve real life problems, okay? So a very large portion of that has to do with problem solving. How do you solve problems, okay? And the problem may be mathematical, logical, or something totally different. Okay, so in this section, we'll be talking about how to solve problems. Now, there are general patterns that you can follow. Okay, so George Polya, he's a famous mathematics teacher, mathematics education expert, and he's written many books. But one of the books is Solving Problems, and there is a thing here called George Polya's problem-solving method or problem-solving process, which has become famous among the math educators. Okay, and this applies to not just math problems, but the problems in general. First, you have to identify the problem. And you say, well, of course, right? Well, it'll be interesting for you to recognize that many times we stress out because we don't know what the problems are, and so we have to identify what the problem is specifically. And once you have a problem, you can solve that. And in fact, places like the research centers and think tanks and consulting firms and even like the space agencies like NASA have hired pure mathematicians, not particularly an expert in the area, but just because mathematicians, we have been trained to identify or to define the problem. Okay, without knowing what the problems are, you really can't solve those problems. And then once you identify the problem, you devise a strategy for solving this. Now, the strategy may require, higher level mathematics or science or whatever. And then you try to carry it out, the strategy. And many times you have to revise that strategy because things don't go well first time. And once you find out the solution or a solution, check the solution. In fact, the solution is not a solution yet unless you verify it as a solution. And then try to explain or interpret the answer. Okay, now this is really general. It doesn't really help you specifically for a particular problem. So what I want to say is in this section, you'll see many different types of problems because that's what life is about, right? There is no magic formula. what's the best way to raise children? I'm telling you very clearly, there is no magic formula. What's the best way to, maintain a good human relation? There's no magic formula. So, but you see different problems. Okay, I mean, the pandemic that we're experiencing is one of those, clear examples of a situation where there are problems. We don't have one simple solution. So how do you make progress? Okay, so here's the idea: flexibility, logic, critical thinking, right? So think flexibly, is that a word? Yeah, logically and clearly, critically, right? Hints and suggestions, all right? So if you have a problem, hard problem, try to consider something simpler, okay? If a problem involves, like, say, 16 different parameters, try to start with 2 or 3 or 4, something simple, right? So consider simpler, no, what did I say? Yeah, consider similar and simpler problems. Also consider something equivalent, like a problem equivalent or with simpler answers, okay? So your answers may be very complicated and messy. Try to replace that, 3.4372 megabytes into, like, let's say, what happens if it's 3? Try to make it simpler. Because once you find an answer to a simpler question, maybe you can find the answer for a more complicated question. Use approximation, all right? And this is, if you go to a grocery store, you buy 10 items, okay, you can kind of look around and see an approximate total, right? It doesn't have to be exact. And many times you don't need to know the exact answer. You can say, yeah, look around, I think it's going to be like $40 or $50. And then you bring out, 20s, or you bring out a credit card, that's easier. But, and then if they charge you, look, it's going to be $300. You say, you know what, something's wrong, right? So often a good approximation is good enough. Not knowing the exact answer is okay. Try alternative ideas and patterns. This is where mathematics becomes a clever sort of a thing. It's not exactly science, because our mathematical solutions are not based on observations often. It requires proof. But sometimes a very clever idea or a completely new way of thinking will give you an answer, right? So, and you may not realize this because of the way mathematics is taught in younger age, or especially in the United States. But mathematics is really a creative exercise, right? How do you find the area of a circle, for instance, or volume of the cylinder? Okay, if you creatively come up with a logical answer, that's what makes mathematics work, right? So creativity is far more important than memorizing formulas. And really, that's what mathematics is all about. All right, often use visual aids, draw pictures, right? I don't know if your math teacher may have told you, like, if you have a word problem, like trains or a farm or building a fence or something, try to draw a picture, because that really helps, right? So I will say, in other words, draw pictures. Many of us are visual learners, and it really helps if you see something. All right, so I'm going to give you several different problems, and some of you, you may think, well, this is really a weird question, okay? But hey, look, this is mathematics, okay? I want you to think in a flexible and critical way. All right, so here's number one. I have changed questions from last semester and the past semesters. So, all right, number one, let's say there are 5 people. 5 people meet for the first time. And let's say there is no, unknown virus going around. So they all shake hands. Remember, we used to do this? Okay, so everybody shakes hands with everybody else, 5 people, right? Exactly once. And now the question is, how many handshakes are occurring all together? Now you say, well, who cares about this, right? But there are all kinds of implications. What happens if 5 computer terminals are there and each of them has to be connected to all the other ones, right? Or if there are 5 countries and every country has to, let's say it's a sport event. 5 countries and 5 national teams are there. Everybody has to play everybody else. How many games occur, right? So there are many important implications of this. What happens if there are like 300 instead? How many? Is there a pattern, okay? I mean, look, if you have 300 people shaking hands, how many? That's really a complicated question. And that's what I mean. Maybe it's easier when you start to think with 5 people or 6 or 2, and then you generalize it, and maybe you can find a formula for the number of handshakes with 300 people, right? Okay, so how many handshakes are occurring with 5 people? Any diagram helpful? Like maybe you can think of these 5 people. You can even give them names, like John and Matt and Susie and whatever, okay? Or you can just call them A, B, C, D, E, because that's much easier when you call them by, something simple, right? Well, A has to shake hands with B. So maybe you can draw a picture like this. And A has to shake hands with C and D and E. Does it help? Not sure. How about B, C? Yeah, I guess maybe this will help. Okay, B shook hands with A already, so that's already counted. B also shake hands with C, D, and E. C has already shaken hands with B and A, so these are already counted, but C and D has to be connected. D and C and E are already connected, right? And then D and E needs to be connected. So that's okay. Now you have to count carefully how many handshakes there are. That's okay, right? Maybe there's a better way to think about this. Draw some pictures. Maybe if one picture doesn't help, draw another picture. Maybe what happens if you put them in a sort of a pentagonal ways? Does it help? A, B, C, D, E. So try to be creative here. Maybe some of you can come up with something even better than this pentagonal or pentagon picture, right? What is helpful for you? Is there any other way to think about this? Okay, so here, for instance, you can say A has to shake hands with B, C, D, and A. All right, again, these may be 5 national teams, qualified for a final round of a soccer events or something, and how many games have to occur if everybody has to play each other. So far, I have drawn 4 lines because A plays 4 teams, right? A plays 4 times. B is already played with A. It hasn't played with B, C, D, or E. All right, and the same thing, if you just keep doing this, C has to play with A and B, that's already drawn there, D and E, and then D has to play with E. Okay, so that looks pretty. And now we're onto something, right? And so think about this. How many edges did I play? Because edges do correspond with handshakes, right? So you can see there are 5 outside here. And then there are 5 inside diagonals we draw, right? And so that looks like 10 is 10 handshakes. That seems to be the answer. And in fact, it is the correct answer, okay? But can you think about why we ended up with 10? Like 10 is good, but how do you even extend this? What happens if it's 6? Do I have to draw a picture every single time, right? And what happens if it's 6? Well, it's going to be a 6-sided figure that would be called a hexagon, right? And then you think, okay, I have 6 outside edges, but how many inside diagonals are there? And this gets a little complicated. Maybe a simpler thing would help, right? Simpler, can you think of a simpler and similar problem? Yeah, how about with 3 people? With 3, A, B, C, so A, B, C, and how does it work? A has to shake hands with B and C, and B has to shake hands with A and C, and so on, right? How about with 4? You have A, B, C, D. You have a square. Okay. Now, again, you may be able to figure out some other clever way of thinking about this. Some of you may already know the answer on how to do this for the number n, of people shaking hands, or what happens if the number is 10. Okay. If 10 people meet together for the first time and shakes hands with everybody else exactly once, how many handshakes will occur? The answer is 45. But how would you know that? Okay. Well, once you figure out the pattern, then there is a quick way of figuring this out. All right. So with 4 people, A, B, C, D, and then you have 2 diagonals, right? So what's the best way to think about this? So 10 shake hands with 5 people. We're trying to figure out how many handshakes will take place with n people, right? Where n is some random number. What's going on here? With 3, let's say when n is equal to 3, then there are 3 handshakes. When n is 4, by the way, did you count this? It's 1. My picture, my writing is moving very slowly here. But if with 4 people you have 1, 2, 3, 4, 5, 6, you have 6 handshakes, and with 5 you became 10, and so there seems to be a pattern, right? And the way you think about this is this. Let's say if you have 5 people, okay. So here's the way in which we drew these edges or lines, okay. So for each person, if you have 5 people, okay, each person has to shake hands with 4 other people, right? For each person, I should say maybe each of the 5 people, each person, let's go ahead and erase this. And maybe I'm again, this is where the pictures could give you a clue, and then you have to think hard on what goes on with this. Okay, so here's where we are at this point. Right, let's say you start with 5 people, right? What I did is from each one, let's say A is there. A shakes hands with everybody except himself or herself, right? So A shakes hands with 4 people. If you start with 5 people, each of these 5 people, each of these 5 persons shakes hands with 4 others. That's the number -1. So if you start with 5, which is your n, then each of the n people shakes hands with n-1 others, right? So that's why you get 20, 5 times 4, because each of these 5 people shakes 4 other hands, and that's 20. But then you realize, well, A has shaken hands with B, but then B is also shaking hands with A. You counted every handshake twice, because A shakes hands with B is the same as B shaking hands with A, right? Remember, each pair of people shake hands with exactly once. So this is too many. We counted every handshake twice. So then you divide that by 2, and that's how we got 10. Now, does that work? So if you start with n, each of these people shakes hands with n-1 other people, but that's counting every handshake or every game twice. So double counting. So you have to divide by 2. That seems like a formula which works when n is equal to 10, right? Because if n is equal to 10, you have, 5. If n is 5, you have 5 times 4. Let's go ahead and write this down. If n is 5, if you have 5 people, then 5 times 4, by the way, this is a multiplication operation here. It's n times n-1, and then divide by 2 is 10. That is the right answer according to my diagram, right? So cool, it is working. How about if n is 4? I know the answer when n is 4, again, because I drew a diagram. Then 4 people shakes hands with 3 others, but that's counting every handshake twice. So you divide it by 2. 12 divided by 2 is 6. And that's the number I got. Ooh, it is working. All right. How about if n is equal to 3? My answer should be 3 because that's what I got up in part B. And if n is equal to 3, this says 3 people shaking hands, each of them shaking hands with 2 others, but that's counting every handshake twice. So you divide it by 2, and that's going to give you 3. Yeah, that is correct. See here, you have just come up with your own formula for a handshake problem, okay? And this, by the way, is the correct answer. You know why? Because this logic was correct. I mean, every one of these n people shake hands with n-1 others, and that's counting every handshake twice. And so you divide it by 2. But the power of mathematics is now you can apply this formula for any n, all right? So let's say 10 10 teams showed up, or 10 people showed up. And if every person has to shake hands or play games with every other person or team, how many? If 10 people show up, then it will be 10 times 9 divided by 2. That will be 45 handshakes, okay? If 12 computer terminals have to be connected to everything else, all 12 have to be connected pairwise to each other terminal, then how many cables do you need? It'll be, what did I say, 12? Yeah, 12 times 11 divided by 2 would be 66. So you need to order 66 cables. So, the far generalization can be possible based on arguments like this. That's very mathematical. It's a great, great problem. Okay, sometimes the problem is more mundane. So here's a problem involving buying and selling. Now, for some of you, and I have taught this problem, I used this problem before, some people find the answer right away, and then some people get really confused, okay? So let's look at this. Well, actually, read this question, and then we'll stop and go to the next segment of the video lesson. But I want to read this first, and then let you think about this. And when you think you got the answer, start watching the next one, all right? A woman bought a horse for $500, but then she sold the horse for $600, okay? Good, she's made some profit. But then she misses the horse, so she buys the same horse back for $700. She lost some money, seems like. But then later she sells it for $800, okay? And that is the end of the series of transactions. In all of these transactions, how much did she make altogether? So this will be the end of part 1. Think about this, and when you think you have the answer, come back and start watching part 2.